So thanks, Tom. Yes, I'm going to talk about 50 years of planetary exploration at LASP in 50 minutes. So that's a minute per year. So I won't be able to cover quite every detail, but if I'm missing something or somebody or you have a question, shout it out. And if you're still at the end of the talk, we're going to have a little time for questions. You can ask me those then. And as far as I know, Cambridge University Press has typeset the second edition of my book, and it should be published in March. You can already order it on Amazon. So if anybody's keen to do that after you hear the talk, then you can order the second edition of Planetary Rings. And I've been here since I graduated from the University of Massachusetts in 1977. And I went to undergraduate and graduate study, and then I came directly to the University of Colorado Laboratory for Atmospheric and Space Physics, and I've been here ever since. And so I admit I've never had a real job, but I've had great fun working with the planetary missions here at LASP. And I'm going to give you just a quick view to cover a number of the ways that LASP has explored the planets in the last 50 years. So if you go to the LASP web page, you can find this chart of missions run at LASP, and they're ranked by the planets in the solar system. And I'm particularly interested in the planets other than the Earth that I'll be talking about tonight, Mercury and Venus. There are other people here at LASP who study the Sun and the Earth, and they'll be giving different talks about LASP history. But each of these blue lines represents a space mission that LASP was involved with. Either we supplied instruments, or we operated it, or in some cases we were in charge of the entire mission. And you look, Mercury is included, Messenger, and Venus. And for Mars, Mariner 6, 7, Mariner 8, too bad about that, it went into the ocean, so I don't have any results for that. Mariner 9, Voyager 1 and 2, Galileo, Cassini, Huygens, New Horizons is on its way to Pluto, and we have also the MAVEN mission, which just launched and is en route to the planet Mars. I also see that Mars 96Z, this is Russian for light, is listed here. That was an experiment, with two experiments we actually built here at the University of Colorado. I hand-delivered to Moscow in my briefcase, and got special permission, of course, from the State Department, Department of Commerce. But unfortunately, instead of landing on the surface of Mars, they went to the bottom of the Pacific Ocean. And that's, before I start, just something to say, there's a little bit of danger with each of these missions. There's some challenge about whether they'll actually succeed in launching, and then when they get to the place they're going to, you're always hoping that they'll work the way that you planned. Usually they do, sometimes not quite, and there are a couple of experiments that stumbled a bit, but we recovered. And in the cases of experiments here, we've had a beautiful harvest of results, knowledge about the planet. So from the very start of the space age, LASP has been involved in space exploration, and that's true with planetary exploration as well. So LASP explores the planets. I'm going to start with Mariner 6 and 7, which were launched in the late 60s, arriving at Mars in 1969, just after the first Apollo moon landing. And this is an old photograph of the Mars Mariner 6 spacecraft, and it carried an ultraviolet spectrometer built here at the University of Colorado. And we started out at LASP with a specialty in ultraviolet spectrometers, and that breaks up the ultraviolet light, which of course humans can't see, but butterflies are able to see light in the ultraviolet. So these experiments that we build here give sort of a butterfly's eye view of the universe, and we developed a specialty for those, and many of the missions to space are interested in that part of the spectrum, the ultraviolet light. And particularly at Colorado, we were always then in an excellent position to compete, to be part of that mission and be selected for numerous missions. And so we started out with these ultraviolet spectrometers here, and they flew by Mars. the first missions to Mars did not orbit or land on the planet, but flew by. And in those days, NASA very cautiously built 2 spacecraft to go to a target. So Mariner 6 and 7 both successfully launched and made measurements of the temperature of the surface and of the atmosphere. And here's a picture. And if we're used to, the modern style of pictures, this doesn't look that impressive. On the other hand, when you saw these pictures come back in the 60s, it was amazing. The first close-up views of Mars, which some people imagine was inhabited by little green men, and the great canals on the surface of Mars, these were not seen by the spacecraft. And I remember very particularly seeing in Newsweek magazine how the early Mariner flybys had shown lots of craters on the surface of Mars, pockmarked, and the headline was, "Mars is like the moon." And this was a disappointment to people who thought Mars might have Martians or some other form of life. But also it was an overstatement. These first missions that flew by only saw one part of the planet, and in this case a particularly cratered part. So these early missions were led by Dr. Charles Barth, who was the first director here at the lab. And his brainchild was this laboratory, and he hired the people, many of whom worked here for decades, some of whom are still working here, including myself. And those people that he hired were able to design and build and also competitively bid for space missions. So Dr. Barth was the director of the lab and also the leader, principal investigator of the early space missions to the planets from here. So here's a Mariner 6 image of the surface of Mars, and I challenge you to distinguish this from the moon. I mean, it's not impossible, but you can see that some of the crater walls are degraded, and this crater has been filled in relative to that one. And so an expert could, just like when a dentist looks at your dental x-rays, he can really tell things you can't. But if you look at this, it really does look like the moon, and some parts of Mars are similar to the moon, and that was sort of a disappointment for people who had hoped to find life, or at least a companion planet like the Earth. But it turned out that, as I said, that was more a defect of the space missions than of the nature of Mars. Now, you probably recognize this. This is the engineering unit for the Mariner 6 spacecraft, which is over in the lobby of the Space Technology Building about 500 feet from here. And if you haven't seen this yet, you might want to drop in during working hours. And it's a full-scale model, including the ultraviolet spectrograph, which was built here. And of course, it's been set up here in our lobby so that it has a good view of this globe of the planet Mars. Well, the next mission to Mars was going to be an orbiter, a Mariner 9 mission, and also NASA selected the University of Colorado to build an ultraviolet spectrograph for the Mariner 9 mission to Mars, and it launched in 1971. Both Mariner 9 and Mariner 8, they were called A and B at that time, but unfortunately, the other one went into the ocean. This spacecraft went to Mars, and the teams were ready to look at close-up pictures of Mars from orbit, but unfortunately, there was a great dust storm. In fact, dust covered the entire planet of Mars, and there was nothing visible. The spacecraft was redirected for a while to turn its cameras to look at the moons of Mars. We got some excellent pictures while the dust began to settle out of the surface of the atmosphere onto the surface of Mars. And you can see that while this is happening, all these little dots are reference marks on the camera. So there's a camera image from Mariner 9, and you can see that there's some spots at this moment starting to appear through the dust. And in fact, there was an immediate argument about this, about whether those were craters like this, they're just starting to appear, or they might possibly be volcanoes. And it was Carl Sagan who made a lot of discussion who had a number of arguments with people that these marks were actually indications of the tops of volcanoes, and they were not impact craters like we saw on the moon. Carl talked about these so much that they got known as Carl's marks for a while, but in any case, when the dust cleared, it turned out that these were actually giant volcanoes. And I'm going to come back to that in a question, because immediately the question was, well, if they're volcanoes, how big are they? They must be big if they're sticking up through the dust clouds. And immediately the camera teams did some triangulation and estimated the heights of these volcanoes from pictures taken at different angles. Here at the University of Colorado, on the team led by Charles Barth, Charlie Hord was one of the co-investigators, and he was looking at the ultraviolet light in the UV spectrometer we had built, and the amount of UV light is proportional to the amount of gas that's above the volcano. So we could measure with the UVS how much ultraviolet light. So this picture is taken in the visible. That would be like what you saw with the naked eye. But in the UV, the atmosphere is strongly scattering, and in fact, as you know, the amount of light scattered follows Rayleigh's law, and it's therefore much more light in the UV that's scattered by the atmosphere. And because of that, Charlie Hord was able to measure the heights of these volcanoes, and he concluded that the tallest one, known at that time as Nix Olympia, or Olympus Mons is the current name, was over 25 kilometers high. And at the Jet Propulsion Laboratory, they had regular press conferences, and he was ready to announce this, but the people on the imaging team wouldn't let him give that result because they said it was obviously wrong because they had gotten a different answer. Well, as it turns out, the camera triangulations were incorrect. The scattering of light by molecules of carbon dioxide, a basic physics process that Charlie Hord had studied, was correct, and these volcanoes do turn out to be up to 25 kilometers high. So there are also other things on the surface, these great canyons. This is near Galvalis, also seen by Mariner 9. And so immediately when the dust cleared, Mariner 9 began to see all sorts of different things, all sorts of features on the surface of Mars, not just volcanoes, but great canyons. The Valles Marineris, the Valley of the Mariners, was also seen. And when the dust cleared, Olympus Mons. And so this is a volcano on Mars about the size of the state of Colorado, and there is a crater on top. So that those people who thought these what was sticking up through the dust might be craters were correct, but it's not an impact crater, it's a volcanic crater, and all of this material here is volcanic lava that's flowed out of the crater on top to form this giant volcano, the biggest one in the whole solar system. Also some chaotic terrain seen on the surface. And here is a picture of Mars with the Valles Marineris, the Great Canyon, the Grand Canyon of Mars, large enough to stretch across the entire continental United States, up to 10 kilometers deep. So that means that our Grand Canyon on the Earth, what we call the Grand Canyon, would fit in one of these tiny little canyons off of the main Valles Marineris. And it's a crack in the surface of Mars created by now defunct stretching and movement of the surface. And the UVS team on Mariner 9, along with Charlie Hord, used the same sort of technique to calculate, again correctly, the depth of this great canyon, which is so large it dwarfs anything we have on the Earth. So I'm still moving at the rate of 1 year per minute, and we're going to go on to the next mission, which is the Pioneer Venus mission. And on this mission, we also built an ultraviolet spectrograph, the UVS. And that mission had multiple parts. There was a bus that carried all of the various probes to the planet Venus from the Earth. And there was a large probe, which was known as the large probe, and then 3 smaller probes that were called the small probes, and one to land night and day and north on Venus. And the 3 small probes and the large probes separated from the bus and hit Venus in different places and descended through the atmosphere to the surface. The carrier spacecraft, the bus, was also instrumented, and it hit the atmosphere of Venus and burned up. So a very productive little mission that originally was to last for just one Venus day, which is 245 Earth days, but actually went for 14 years. And here I have Dr. Ian Stewart. You probably recognize him. He's still working here at LASP. This is him pointing out a piece of data from Pioneer Venus, and this is some Venus night glow here, nitric oxide emission. So on Pioneer Venus, we looked at the atmosphere of Venus, and particularly the ultraviolet spectrometer is sensitive to a number of gases in the atmosphere. So we saw emissions from carbon dioxide, carbon monoxide, nitric oxide, and also from the molecule sulfur dioxide. You know, sulfur dioxide, that's what comes out of coal-fired plants that don't use very clean coal. And you know that on the Earth, the emission of sulfur dioxide leads to acid rain. And here, one of the developments we had back in 1978 was to see that the same cycle of sulfur dioxide in the atmosphere of Venus was being broken up by sunlight and creating sulfuric acid. And in fact, our results here showed that the planet Venus has the worst case of acid rain in the entire solar system. So we also used radar to look through the clouds of Venus. You can see for yourself they're quite opaque. But with radar, we were able to go send radiation and bounce it off the surface and measure the topography of the surface of Venus. And it has several continents and lots of lowlands. It's not quite as distinct a distribution of altitude as on the Earth, where a quarter of the Earth is raised up the continents and 3/4 the ocean bottom is low. But so there's not as big a difference between the highest parts and the lowest parts, but there's a similar set of rolling plains, which are, if Venus had any water, which it doesn't have very much of, would be oceans now. And so I want to say a little bit more about sulfur dioxide. So here's a graph of years starting back when Pioneer Venus went into orbit, which was in December 1978, coming up to the present time. And on the vertical is plotted the amount of sulfur dioxide gas in the atmosphere. And you can see that when we arrived in the late 70s, there was a very large amount of sulfur dioxide, which has been steadily declining until 1994, which was when the Pioneer Venus spacecraft burned up. It was the end of the mission at Venus. And we thought that we'd never see that again, which is true, except for the Europeans sent a mission to Venus in 2006 called the Venus Express. And it saw another increase and then a decline in sulfur dioxide. So you might imagine, are the Venusians firing up the dirty coal-fired plants every 30 years? There's another way that we get sulfur dioxide in the atmosphere of the Earth, which is through volcanic eruptions. And the Pioneer Venus data suggested there had been a huge volcanic eruption around 1978, where the sulfur compounds, sulfur dioxide, were gradually converted into acid rain in the clouds of Venus. And now it looks like there was another similar episode, potentially of a volcanic eruption. And we see volcanoes on Venus. This is the volcano Mons, and all of these yellow, the colors are artificial, but all these yellow colors based on radar images from the Magellan orbiter are volcanic flows. So you could imagine if Mons had erupted in 1978, that it would have injected sulfur dioxide gas, which would have turned into acid rain and explained the behavior we see. And if that's happening, it could have happened again. Well, unfortunately, we don't have quite enough information to really confirm that. And other people suggest, other people than myself suggest that maybe it's some sort of atmospheric phenomenon, which is possible, that's mixing up the sulfur dioxide. We don't actually have to have an injection from a volcanic eruption. But nonetheless, one of the findings from Pioneer Venus, which has now been confirmed by the European Venus Express mission, is that periodically, every few decades, there's sulfur dioxide that's injected into the middle atmosphere of Venus, and there's still a dispute about whether that's from volcanic eruptions or some more prosaic climatic behavior. So I want to move on to the next mission, which is the Voyager mission. So we started out in the 60s with Mariner 6 and 7, in the 70s with Mariner 9, then Pioneer Venus. In 1977, the Voyager spacecraft, once again, 2 of them were launched toward the outer planets. And we also had an experiment on this mission. Can't see it very well here. It wasn't a UV spectrometer. It was a photopolarimeter called the photopolarimeter subsystem, or PPS for short. And its job was shaped about the size of a fruit can. And its job was to measure very dim light signals from stars and from gas in between the planets, and also from zodiacal light from dust in the solar system. And I have to say, you know, I'd said earlier that there were there's some danger in space exploration, and the photopolarimeter system, the PPS, experienced some of these dangers. It was meant to look at dim objects, but for some reason the spacecraft was pointed, so it looked at the sun for several days on Voyager 1. After that, the detectors were burned out, never took another measurement. And on Voyager 2, the mechanical parts of the experiment got stuck, so it had a wheel which would turn to give you different colors of light, and the wheel stopped turning. We got it started again, but then it would only turn to 2 particular wavelengths that it had chosen, not us. So I was just reading the official Voyager book, Voyages to Jupiter and Saturn, and the whole section about the University of Colorado photopolarimeter subsystem is about all the things that failed. And I was working here at that time, and the fellows of LASP used to have a special lunch. We don't have fellows anymore, but those of us who were younger, we refer to ourselves as underfellows. And the underfellows also had a lunch, but it was just in the cafeteria. And I was sitting in the cafeteria, and somebody was quizzing us about, you know, one of our colleagues here at the university, about what was the story about the photopolarimeter subsystem, about the PPS. And he said, well, what about this? I said, well, we tried that, it didn't work. He said, what about this? Oh, we tried that, that didn't work. Did you send it a command to do this? Oh, yes, we sent that command, it didn't work. And then I was sitting with Bob West now at the Jet Propulsion Laboratory. He said, in fact, things got so bad that not only were we messing up our own measurements, but our signals were messing up other people's measurements. And so therefore, they sent the jettison PPS command. So you have to imagine, I guess our colleague imagined there were, you know, pyrotechnic bolts that would get rid of this, but I was able to say, well, that didn't work either. Anyway, Voyager has left the solar system. If you've been paying attention, it's now left even the solar system's sphere of influence, the heliosphere, and it's carrying a record on it. And this is old technology, I know. Nobody has records anymore, but the Voyager spacecraft, each one of them has a record. And you can see immediately on here there's some universal language which is translatable by any intelligent system. So down here is the wavelength of the hydrogen hyperfine transition, and here's the location of our sun and the 8 nearest pulsars. And here are some directions about how to use the record and a preamplifier not supplied to listen to what's on here. And what's on here are greetings from all the nations on the earth that are recorded, and if you supplied, I guess they supplied a stylus, but you have to supply your own preamp and speakers. If this were discovered by aliens, it's left the solar system, they could you know, plug that in, spin the Voyager record, and listen to all of those greetings. And it's not just that, it also has what Carl Sagan called Earth's greatest hits. Everything from Bach to Chuck Berry. And this is all on here. And you can buy the record. I have a copy of it. I don't know if you can buy it anymore, but you can buy this record. If you have a record player, you can still play it and hear not only those greetings, but all those great songs that are written by humans. And there was on Saturday Night Live a show, the Weekly News, where they said that aliens had actually found the Voyager record, and the first message had come from the aliens, which was, "Send more Chuck Berry." And here's Charlie Hort. I mentioned him earlier. He was the principal investigator on the Voyager PPS. And, you know, we were not very kind, and he wasn't the first principal investigator. The first principal investigator had lost his job. He had been canned based on some of these failures with the mission. And not only had we lost our principal investigator, but a number of the co-investigators had been canned. In fact, you know, at a different lunch, a different Underfellows lunch, we were talking about all the people who had been canned on the PPS team. In fact, there ought to be a canned PPS team. And in fact, thinking about it, those people were probably better qualified than us, who had the current responsibility. There were more of them, and they're better qualified than us to run this, but we never got to be a member of the canned PPS team. And later, Charlie Hort took on the lead for the ultraviolet spectrometer. We got another principal investigator who I'll show you in a second or two. But on Voyager, there were great discoveries, and one of the real early discoveries was when we were flying by the Jupiter system. We didn't know quite what happened. Charlie Hort was the principal investigator. He'd been out at JPL. He had returned his rental car to come back to Colorado for the weekend to fly from LAX to Denver. He'd already checked his luggage when he was paged at the airport. This was 1979, days before the cell phone. So he was paged at the airport, and they said, "You have to come back to JPL." He said, "Why?" He said, "We can't tell you." And so, sure enough, he rented another car. His luggage went on to Denver, where Karen Simmons, is she here? She met it at the airport and put it back on the next plane to LAX. So he got back out to him at the Saga Motel in Pasadena. But when he got back, it turned out that somebody had discovered volcanoes erupting on the moon Io of Jupiter. And the reason this was going to be a big release, it had been predicted in some way, but not really believed. And here's just an example of one of the pictures. This was not the discovery picture, but a picture of the eruption on the moon Io. And here's the volcano, one of the volcanoes. There's another one on the limb, putting out this plume of gas. And the reason why Charlie Hort was called back is because then there was going to be a big press conference, and they couldn't tell him over the phone because that would have broken the excitement. And particularly, the photopolarimeter system, which had all this bad press and everybody hated, had one particular channel which was able to see the yellow line of sodium. And so they wanted the PPS data to see if we saw sodium in this plume. So he had to go back, and a day or so later he received his dirty clothes back from California. So there were others who were working. The next principal investigator was Lonnie Lane, and here I am talking to him in 1981, and we were discussing the planet Jupiter. This, of course, is the great red spot, and here at the lab we had the public information movie that was made from the Voyager approach playing. So you could, if you went to the lobby of our building on campus, we're not occupying anymore, but the old LASP building, you went there, you walked in the door, there was a constant loop of the swirling hurricane that is the great red spot on Jupiter. Just to give you a sense of scale, it's about 3 times as big as the Earth. So you fit 3 Earths in here. It's an immense hurricane that's been going for at least 3 centuries. And I'm sorry, that's the great red spot. This was called a white spot, a white oval. Anyway, in here, and these little curlicues swirled all around. But that wasn't the best thing. The best movie was actually this shown in blue, which was known as the blue movie, and through the blue filter. And people were looking at that and other data that came back from Voyager. Here you can see Charles Barth again, and they're looking at the first traces of the first stellar occultation by Saturn's rings that was observed by Voyager. And you know, I have to admit it, and I apologize, I should have already, but if you do UV spectroscopy, what you make are squiggly lines. So our data are just little squiggles, and here you can see them here. We worked so hard sometimes to turn our squiggly lines into pictures, and we've been partly successful in that. But the only way to really get beyond that is to have an imaging spectrograph, which is one of the things that we've developed from the original UV spectrograph. So when we get to Saturn, the next mission after this one, we actually had an imaging spectrograph, and we didn't have to show other people just long sheets of paper with little lines on it. Okay, well, the Voyager space mission originally was intended to go to Jupiter and then to Saturn, but Voyager 2 was redirected to go on to Uranus and then Neptune as well. So one spacecraft took a grand tour of the solar system starting in 1977 with launch, flying by Jupiter in 79, Saturn in 1981, Uranus in 86, and Neptune in 89. So we sort of got 4 planets for the price of one. That was not only a good bargain, but because the experiments, and in most cases the experimenters, if the team hadn't been canned, most cases the experimenters were the same, and so people got to do the same measurements and experiments and the same analysis on all 4 of the giant planets, which is an immense scientific return from one space mission. And Fran Bagenal was also working on that, and her expertise was the planet Jupiter, and particularly the moon Io and its Taurus. Oh yes, so here is that famous blue movie, and it's just taken through a different filter on the camera, but the same sort of thing, the great red spot here, a white oval, and swirling bits of Jupiter's atmosphere. So after Jupiter, we went to Saturn, and then to Uranus, and then to Neptune, where this image was taken of bluish Neptune with some white clouds in it. And of course, these clouds are not water clouds, they're methane. So when you go back outside tonight and you see water vapor freezing in the air, just be happy you're not on Neptune where methane freezes in the air. Okay, and the next mission is the Galileo mission. So we talked about missions to Mars and missions to Venus and missions to Jupiter, Saturn, Uranus, and Neptune. And this Galileo mission was a mission to the planet Jupiter, which went into orbit about it. So this was an advance in our scientific capability based on technical capability. Originally, we just flew by the planets. We got a snapshot. Sometimes that didn't tell you the right thing or just about one part. But Jupiter was the first mission to orbit the planet. I'm sorry, Galileo was the first mission to orbit the planet Jupiter. And you can see in this photo, it's not looking really good. The antenna hasn't completely opened up, which was a problem. And we were never able to fix that. And that meant that the data from the planet Jupiter, most of it was not sent back to the Earth. We only got about 10% of the original data volume, but a very carefully selected 10%. And so Jupiter, the Galileo mission, when I arrived here in 1977, Charlie Horde had just learned that we had been selected to build this experiment. But through a number of delays, including the Challenger disaster, it didn't launch until 1989. It did not arrive at Jupiter until 1996. So I had been here for almost 20 years after the announcement that we had been selected to build a UV spectrometer for Galileo. And then it circled Jupiter, orbited Jupiter, went by its moons for about 8 years before ending up as a meteor in the atmosphere of Jupiter. So here another couple people, Charlie Horde again, and Gene McNutt, who is the project manager here on the building of the ultraviolet spectrometer, the UVS for Galileo. And Charlie Horde was my first boss here. And then Gene McNutt was also my project manager when we built the ultraviolet imaging spectrograph. So here they are in an old office in the 55th Street building, now long gone, showing off the ultraviolet spectrometer, which then went into orbit eventually around Jupiter and made a number of spectacular discoveries about the environment of Jupiter and particularly the Io Taurus. So Galileo also included a probe which descended into the atmosphere and returned, even though not as many as we had originally planned, a number of really spectacular views of the moons of Jupiter. And this is the moon Europa. Looks like people have been using their snowmobiles to drive across it here. It's an icy surface, and Europa is one of the major targets now for the next planetary mission, the next big one, which would look at the moon more closely to see if there's an ocean buried underneath the ice, and if so, how far. And this is one of the things that still gets people excited. Remember how people were excited to find life on Mars, or at least to search for it. This is another place where if there's water underneath the surface of the ice, like in Antarctica, you might find living organisms there too. So I want to say a couple of things about Mercury. So we're getting sort of there. We've got Venus and Earth and Mars and Jupiter and Saturn and Uranus and Neptune. This is the messenger mission to Mercury, and the university, LASP, also has an experiment on Messenger, which at this very moment is circling the planet Mercury and taking, these are photographs of the surface, but our experiment is a spectrometer, again, which is measuring the emissions from Mercury's very tenuous atmosphere. But here are some pictures of the crater Lennon, named after John Lennon, and the crater Bartok, named after Bela Bartok, on the surface of Mercury. And so Messenger has been our best opportunity. It's been orbiting Mercury for several years, and it's our best opportunity to see that close up. And once again, there's a spectrometer on there built here at LASP at the University of Colorado. So I've talked about a bunch of missions. This next mission is called New Horizons, which is a mission to the planet Pluto, or at least when it was selected, Pluto was a planet. Now Pluto has been demoted, no longer a planet, but maybe that's why there's this dashed line here. But in any case, launched in 2006, and it's on a long journey to get to the former planet, the body formerly known as the planet Pluto, which would be on Bastille Day just next year, just about a year and a half from now. And that is a spectacular achievement of a spacecraft that goes very, very fast out to Pluto and then is able to go by it, take some photographs, and then look back at the sun and the Earth. And so on this scale, we've gone from the sun, and now we see there's been LASP experiments at Venus, at Mercury, of course at the Earth. I'm not talking about them in this lecture. At Mars, Voyager and Galileo went to Jupiter, and Voyager and later Cassini went to Saturn. Voyager went to Uranus and Neptune, carrying the CU experiment, and now we have CU experiments and a CU experiment on the way to Pluto. And you might ask, well, what is that experiment? And it's called SDC, which stands for Student Dust Counter. It's an experiment that where students here at the University of Colorado play a major role in the design and fabrication, and also in the analysis. And it counts the number of dust particles in space that's passed through by the New Horizons spacecraft. And I continue to show pictures, and of course the principal investigator is Mihai Harani, who's also in the room, who's pointing out some piece of equipment. This is not the student dust counter because it's much too big, but he's the one who's in charge of that particular experiment, which is a LASP experiment going to Pluto. And I think if you've been keeping track, that covers all the planets. So we've got LASP experiments over a period of 50 years being built, starting with UV spectrometers, but various sorts of experiments that are being built, placed on missions that have gone or are going to all the planets. And just the very most recent one of these is the MAVEN mission, which just launched last fall in November toward Mars. And if you read all of this, you'll see that NASA's MAVEN is going to study the Mars atmosphere, and particularly how Mars has lost its once thicker atmosphere and has changed from a time when it must have been much nicer to be on Mars, and maybe even life evolved there at one time, to the current dry, cold environment. And this is a particular case. We've graduated here from LASP from proposing and building experiments for space missions to proposing and building entire space missions. And so this space mission, MAVEN, is a mission that is led by Bruce Jakosky, who's the principal investigator. And he's in charge of this mission, and LASP is in charge of the whole mission. Even we don't build every piece of it. We buy some of it, and some of the supplies, experiments supplied by other institutions. But we've gone from building single experiments that go to the planets to building whole missions and running them that go to the planets. And of course, I have to mention that we've developed along the way the capability not only to build these experiments, but to operate them in space, and also naturally to get the payoff from that exploration, which is to learn the scientific results. So now I want to talk about what I admit is my most favorite mission, which is the Cassini mission to Saturn, which was launched on October 15, 1997 from KSC. And here's a picture of that night launch, a beautiful sight. And the somewhat circuitous path, maybe a billiard shot off a couple of walls, using the planets to propel us on to Saturn, where the Cassini spacecraft arrived in 2004 with an experiment here, the ultraviolet imaging spectrograph. So as I said earlier, we went from ultraviolet spectroscopy to ultraviolet imaging spectroscopy, so we can make pictures of the planets in the ultraviolet, truly take advantage of that butterfly's eye view. And here is the UVIS team. I'm in the back, and you can see Ian Stewart here, and Ralph Reika, and the late Michelle, and George Lawrence, and Justin Mackey, who was a student here, now working at the Jet Propulsion Laboratory, Uwe Keller from the Max Planck Institute in Lindau in Germany. And it was tough with our science team. These were the people who, over a period of decades, wrote the proposal and then designed the experiment. It was built here at LASP, and this, you can see the Mariner 6 mock-up behind it. So this was over in the lobby of the Space Technology building, and built this, and since then have been operating it in space and analyzing the data. Hard to get all those people together in one room. Candy was there, but Bob West unfortunately didn't make it for this photo. But luckily, Justin Mackey, who is a student here, there's Justin, was able to Photoshop George Lawrence in, and Bob West also. Unfortunately, we only had an upper half photo of Bob West, but luckily Hans Lauka's legs were available, and so those were used again for Bob West's legs here. And so this was the team behind the ultraviolet imaging spectrograph UVIS, which was one of the 12, and is still one of the 12 experiments on the Cassini orbiter, now in orbit around Saturn. I just want to show you a few of those pictures, and these are all from the so-called Cassini Hall of Fame. So if you Google Cassini Hall of Fame, you'll find the 100 best pictures from the Cassini mission, which I've selected a few of my favorites. So this one was when we were approaching the planet Saturn in December 2003, and we were able to get every day a better and better view, and with the ultraviolet spectrometer we were able to map out the emissions, discovered a huge cloud of oxygen around Saturn, which later we learned after orbit insertion. This artist's conception, no photographs there. On June 30th, 2004, just about 10 years ago, we went into orbit. We took close-up pictures of the rings of Saturn. And this is somewhat of an artificial picture, lots of ways, but at least the colors are truly artificial, because who knows what colors the butterfly sees, but this is what we imagined the artificial colors might be. And here, the moon Enceladus, like the moon Europa of Jupiter, likely has water underneath the icy surface. And here we see jets of water shooting off of the surface, not only into space, but escaping from the moon's gravity. And so what a spectacular finding. We were able, with the ultraviolet imaging spectrograph, with UVIS, to measure the amount of water coming out here. And when we did that, we were able to calculate the amount of oxygen that would be produced by that. And it turns out that this discovery, which was made a couple years later, exactly explained our earlier discovery of the oxygen cloud. So that was very gratifying, not only to discover an oxygen cloud and to measure the water vapor, but to show that these molecules of water that are broken up by sunlight make the huge cloud of oxygen we saw on approach. So Saturn has a lot of moons, 63 at last count. Titan is the largest moon of Saturn. It's a moon with an atmosphere of nitrogen, very similar to the Earth's atmosphere, although a lot colder. And, you know, ice at the temperatures of Saturn's moon Titan, the surface temperature is about 95 degrees above absolute zero. It's almost as cold as liquid nitrogen, which the dermatologist keeps at his office. And at that temperature, the surface is covered by water, but the water is frozen, hard as rock. But about 3% of the atmosphere is made up of methane, and the methane in the atmosphere of Titan has a role that's very similar to the role of water cycle on the Earth. We have methane clouds, we have methane rain, and methane lakes, and methane rivers, and as the University of Hawaii professor quipped, the rain on Titan is predominantly methane. And so we circle the planet Saturn. We have been for 10 years. We hope for another 3 or 4 more years if our funding holds out. We've got plenty of power and fuel, but you know, since all of the work that I've talked about here is supported by one government or another, we have to depend on the U.S. government to continue sending us the funds to operate and analyze the data from Saturn. But it looks pretty good. We're writing another proposal for an extension for the last 3 years of the Cassini mission, and then it too will end up as a meteor, will burn up inside the atmosphere of Saturn, but not before having an orbit that takes it inside the ring, so it passes in between the closest ring and the atmosphere of Saturn some 22 times. So we're looking forward to continued funding and getting really spectacular views of the planet and the rings close up. Now, I just have to show you a couple of these. We watched the first day of spring on Saturn, and this is the shadow of one of Saturn's moons, Mimas, falling across the rings of Saturn. This is something that only happens every 15 years when the sun is low enough in the sky, as seen from Saturn. It's directly on the equator, on the equinox, and the moons all cast long shadows. You can probably see right here that, like this triangular shadow, there are lots of little triangular shadows here. Those are all little tiny moons that are embedded in Saturn's rings. Each of them is casting a little shadow too, another phenomenon that can only be seen every 15 years. So I consider myself particularly lucky to be on this mission, and also to be on there at a time, on the Cassini mission at a time that we got this spectacular once-in-a-lifetime view. And you might ask, where do those little moons come from? And my particular idea, if you ask me, that's another seminar, I can give it another time, but my particular idea is that there's a sort of ecology of clumps in Saturn's rings that's related to the ecology of foxes and hares. That's a different talk, though. So I want to come back to this picture again. You know, Bob with his artificial legs, George Lawrence inserted in there, the rest of us sitting around this tiny little experiment. Some people ask, you know, how can something that meets FAA regulations for carry-on luggage cost $15 million to build? And this is the example here. Of course, I mean, it did meet FAA regulations, and it could fit under a seat, but we didn't travel with it that way. It had to have a great big protective case on it, and when we sent it in air cargo the first time we sent it to JPL for initial checkout, but unfortunately the case came back dented. And so Gene McNutt said, we're never going to do that again. And so Mr. UV experiment made one-way trip Denver to LAX, and from there to Saturn. So I want to say that, how is it that we've been so fortunate here at LASP to be involved with all these space missions, to all the planets, and that's why I've got this picture up here to remind me. It's because of the people here. It's not because of that little piece of aluminum that cost $30 million. It's because of all those people. Some of those pictures I've shown you, Charles Barth, Charlie Wood, Ian Stewart, and others here, and particularly Barth, who assembled the original team and has been leading the lab over some decades until his retirement in successfully proposing. So in giving us the chance to build and learn and develop the experience of building these experiments, and then these teams of scientists, engineers, operations, managers are able to, next time around, when the next opportunity comes, which it has again and again in my almost 40 years here, the next time around we're well positioned to build what NASA needs to build, first to win the contract, and then to deliver that and operate it in space. So, thanks to all of those people shown in the picture, and all the people at LASP, who are those who have been able to allow LASP to explore planets for 50 years. So I've told some stories and some jokes, and wanted to say something, a lot about the past I've said, but something about the future. So LASP has sent space experiments to all the planets, and Pluto too. And originally UV spectroscopy was our specialty, but that led to imaging and infrared observations, dust measurements, particles fields, and to leading complete missions. And our strong crew here, I'm just going to say this again, means we're well positioned. We have the experience that combines engineering, research, and education. We not only deliver these experiments for the National Space Program, but we train students while we're doing it, and we reap the advantage of students' salaries. The students are, in many cases, more capable than some of the people that you might hire on the street, but also, while they're learning, they're very much less expensive. So we have the advantage not only in education, but financially from that here. This combination of engineering, scientific research, and education is pretty much unique in the country, maybe even in the world. And that's the team that we built to do these things is positioning us for future competitions. But unfortunately, planetary exploration is more expensive and it's harder now. It's just harder because the easy questions have been answered, and now we have tougher questions that require bigger and more expensive missions and experiments. But I speak for many of us here, we plan to continue to compete in every one of these experiments that I'm talking to you about, and the whole missions was a competitive process. We had to win out in the competition to be selected for those NASA and other contracts, and we intend to continue to win future opportunities and continue to explore the planets. Thanks for your attention. So I'm glad to take questions or comments or corrections. Yes?
You showed a graph earlier about the concentration of sulfur in the atmosphere of Venus.
Yes.
And I was surprised to see it varies so much. And that poses the question, what is the mechanism by which sulfur gets removed from the atmosphere, given that Venus is 900 degrees Fahrenheit, so you can't really have rain. And I just wondered, how does it precipitate out?
So several questions. So first, the sulfur dioxide is chemically oxidized and hydrated to sulfuric acid. The sulfuric acid gas condenses into sulfuric acid aerosols, and then they do fall, but they evaporate before hitting the surface. It's like rain in the desert. And so there's a cycle of photochemical production, condensation, deposition, and evaporation. And that cycle is maintained by the continuing input of sulfur gases from volcanic eruptions on the surface. At the same time, the sulfur dioxide vapor, when the sulfuric acid is low enough in the atmosphere, it thermally decomposes back to SO3 and H2O, and the SO3 combines with rocks on the surface of Venus. So we have continual gas, sulfur coming out of the surface, forming the clouds rain out, they evaporate, but the gases combined with the rocks on the surface to make sulfate. So there's a continuing process of sulfur coming out of the interior, making the clouds, and coating the surface with sulfates. Yes, sir.
Thanks. It's a very fun talk. Two questions about the volcanoes on Mars.
Yes.
How do they get so big? Is it just the lesser gravity? Or?
No, it's not the lesser gravity. But so here on the Earth, if you look at Hawaii, Mauna Kea is one of our biggest volcanoes. If you look at the Hawaiian Islands, you see a series of islands, and that's because the Earth's surface is moving through the plate tectonics. So there's a hot spot underneath the surface of the Earth where molten lava is coming up and breaks through the surface of the Earth and you get a volcano, and then the Earth moves and you get another volcano. So on Mars, there's no plate tectonics. So there's no successive line of volcanoes. All that eruption occurs at one particular location and builds these giant edifices, these giant structures.
But on the map, the graph, there were two other calls Mars that looked as if they were in a line, but they weren't put that by the
So there actually are 4 of these marks, and they're all in a bulge, a particular region on Mars called Tharsis, and they're all related to uplift in that region, and also the cracking that leads to the Grand Canyon, the Valles Marineris. So this is not my particular field, but I find that a convincing explanation that the structure of Mars without the moving surface, without continental drift, leads to giant volcanoes in those regions where the interior is uplifting. In that region, we see 4 marks, 4 volcanoes there. Yes?
When Pluto was demoted, was there any serious concern that the funding suddenly should come from a different subgroup of NASA?
No, apparently not. So the funding was secure, the mission wasn't canceled when Pluto stopped being a planet. Although Alan Stern, the leader of that particular mission, and a former student here at the University of Colorado, and a former student of mine, resisted that very strongly for just that reason, but he's been able to survive it. The mission is still going, he's still leading it on to Pluto, and just in a year and a half, it's going to fly by, a very spectacular moment where we'll have results from our experiments and the other experiments on a place in the solar system we've never been. Questions? Well, if not, thanks again. Oh, you have one more question.
Yeah,
This will be the last one.
on Mercury, there was a crater labeled the crater Bartow. I'm a musician. Is that a Bela Bartow?
Yes.
Huh. Why? I mean, why not? Of course, it's a crater.
So the International Astronomical Union, the same one that demoted Pluto, so people are angry, they also decide the names of all features on planets. They have a particular commission, number 15, on planetary nomenclature, and they like to have a sort of style of nomenclature. So Bartok and Lennon are 2 musicians that are immortalized on craters on Mercury by the International Astronomical Union. So thanks all for your attention. Drive safely.